Hello class. Properties of functions. A function is increasing on an interval if f of a is less than f of b for all a less than b in that interval. Well, the interval we're talking about is an interval of x coordinates. And to be increasing really just means that the graph is going up from left to right. And I say left to right because x increases to the right. Y increases going up. To look at a function like this and to determine where it's increasing and decreasing is rather straightforward. You just imagine that you were walking along the function from left to right, walking this direction. If you're walking uphill, then you're on an increasing portion of the function. If you're walking downhill, you're on a decreasing portion. So notice that from here to here, this portion of the graph is increasing. Notice that I don't end the graph here with the solid dot like I do on the right. That's suggesting we should always assume then that this pattern just continues. So that if we saw more of the graph, we would just continue. If we start as far left as negative infinity, and then we walk this direction, we will always be going uphill. And we'll reach the top of the hill right here when x is negative 1. So I'm going to say something like this. F is increasing. For, or over, or on, or if. There's lots of prepositions you can say here. And then we say for x is an element of, and then we're going to give an interval from negative infinity up to negative 1. And let's just give open intervals. This word here, open interval. Open, when referring to an interval, means parentheses on both sides. So this is an example of a closed interval. This is the corresponding open interval. And if you put bracket on just one side, or it's partially open, partially closed. So we're going to give answers that are open intervals. So I'm going to highlight the increasing portions in pink. So we have all of this graph up to right there is increasing. The next part that's increasing is from 3 to 4. Union 3 to 4. Okay, so if I were to take any a and b in one of these two intervals, and they got to be in the same interval. You don't want to pick an a here and a b over here. Pick any one interval, pick two vertical lines, call one of them x equals a, and another vertical line. So just make sure that b is larger than a. In other words, b is further to the right of a. That's what we're saying right here. And if I do pick a b larger than a, then notice that the output of b, so f of b is up here and f of a is down here. The y-coordinate of the one on the right is higher than the y-coordinate of the one on the left. So all that we're saying here is that if you pick an x that's larger than another x, then the corresponding y should be larger than the other corresponding y. That means that the function's increasing on that interval. And of course we have a second interval over here where it's increasing as well. Same thing over here, pick any a and b over here on this interval, and if b is larger than a, then f of b will also be larger than f of a. Another way of saying this is that if you go further right in the graph, then the graph goes further up, and that would be an increasing portion of the graph. But the key is to think left to right. Even though sometimes it's tempting, I put this little arrow down here, and that makes people think that the graph is being drawn right to left. But when you're talking about whether a function is increasing or decreasing, you should always imagine going left to right. Okay, the decreasing portions, we have a decreasing portion right here. There's only one decreasing portion, and we would say f is decreasing for x in the interval, and then think x coordinates, right? So we started here, we ended here. It's negative 1 to 3, and make it an open interval. And what this statement up here is saying is that if you take any b that's larger than a, so here's a b, here's an a, in this interval, it'll be the case that f of b is lower than f of a. That's what this is saying here. F of b is less than f of a when b is more than a. And then the other possibility is that a function is constant on an interval if f of b equals f of a for all a and b in that interval. So the only constant portion is right here. And we will say f is constant for x in the interval, and the constant portion started at 4 and ended at 6. And so if you take any a and b in here, it doesn't even matter which one's larger, and you get the exact same height, then it just means the function was constant on that interval. The output of a function, f of a, is sometimes called the value of the function corresponding to x equals a. So this word value is used often, and it represents the y-coordinate. And because it's a function of x, there's only one value for every input. That's the definition to be a function. A point a comma f of a is called a local or relative maximum if f of a is larger than all outputs in some open interval containing x equals a. This is just a fancy way of saying it's the highest point in the area. A point a comma f of a is called a local or relative minimum if f of a is smaller than all outputs in some open interval containing x equals a. So it's the lowest or smallest output in its immediate area. Okay, let's take a look at this image here and identify the local extrema. The word extrema, this is a plural word in English. The singular is extremum, and extremum is a singular word for maximum or minimum. So extrema means all maximums or all minimums. It's plural and it refers to both maximum and minimum. You can also say maxima and minima. That's another way to pluralize minimum and maximum. We are first going to do the instructions that find all local extrema. That just means find all local maximums and or local minimums. These are very easy to spot. If you see the top of a hill, like it appears to be this point right here, -1, 1. It's the highest point in its immediate area. Now, it's not the highest point of the entire graph, because there's points over here that are higher, but it's the highest point in its immediate area. All of its neighbors are lower than it. That means this is called a relative or local max, REL max, relative max. Over here is the bottom of a ditch. It's the lowest point in its immediate area. It's the point 3, -1, and this is a relative min, because it's lower than anything in its immediate neighborhood. Or when this definition says that it's, let's look at the minimum, for example, that f of a is smaller than all outputs in some open interval containing a. So a is 3 in this case down here, and if you do some open interval containing 3, just focus on that part of the graph, that the point in question, the relative min, is the lowest of all points on that portion of the graph. We can also analyze the endpoints if they are included. Now let's look at this endpoint here first. There's nothing here. There's no point. There's no y-coordinate. Therefore, we cannot call that point a relative max or a relative min. There's just nothing there. But over here, we have a solid included point. It's at the point -5, -1. And there is no graph over here on this side of it. So it is the lowest point of all the points in its neighborhood. So endpoints, if they're solid, can also be considered relative maximums or minimums. In this case, this is a relative min. And that's all of the relative extrema for this particular function. The largest value of a function. Now, value is that word that means y-coordinate. The largest y-coordinate of a function, or the largest output of a function is another way to think of that, if it exists, is called the global or absolute maximum value of the function. And the smallest value of a function, if it exists, is called the global or absolute minimum value of the function. So the lowest y-coordinate possible on this graph is -1, and it occurs twice. So we're going to say that the absolute min is, and then we just give the y-coordinate, that's typically how this is done, is -1, but we can also say where it occurs. Notice it occurs twice, this point and this point. So the absolute min is -1, we give the y-coordinate for that, and we say it occurs at, and then we give the x-coordinates. So I'm going to go ahead and specify that -1 is a y-coordinate, and it occurs at x equals -5 and at x equals 3. And the absolute max, what's the point on this graph that is the highest point of the entire graph? Well, if this was solid up here, then that would be the highest point of the graph, but it's not solid. So then you might say zoom in and pick the point that's just below it. But if you keep zooming in, you're going to be able to notice whatever point you say, you're going to be able to find one that's higher. Now, that hollow location is at height 3. So if you were to say that the highest y-coordinate, therefore, is 2.9, then I could say, no, it's 2.99. And then that's not the highest either, because I could say 2.999. And we could keep this up forever. There is no one y-coordinate that you can say is higher than all the other y-coordinates of this graph. You can always get closer to 3. So this graph actually has no absolute maximum. Now, another way to determine what the absolute max and absolute min of a graph is just to look at the range. The lowest y-coordinate in the range is -1, and it's included, and the highest would be 3, but excluded because of the hollow point. But when you have a range that's a partially closed interval, if it's closed on one side, then that's going to correspond to the lowest y-coordinate possible, so the absolute min will be -1. But the fact that the range ends on a hollow, or parentheses, means that there will be no absolute max. A function of x is even if f of -x equals f of x. Such functions are symmetric about the y-axis. A function is odd if f of -x equals -f of x. Such functions are symmetric about the origin. Determine whether each function below is even, odd, or neither. Then use technology to graph each function and observe its symmetry. Let's start with f of x equals x squared minus 3. The way to determine if a function is even or odd is to see whether one of these two statements is satisfied. If neither one of them is satisfied, then we say neither. And the way to do that is just to calculate the left side and see if we wind up getting one of these two sides over here. So in other words, just do f of -x. We're going to evaluate this function at -x, which means every single x in this statement needs to be replaced with -x, and use parentheses, because the exponents might affect whether the negative stays or not. Now, in this case, when you square a negative, negative times a negative is a positive again. So the negative here is going to be canceled by the squaring, and then we're just going to wind up getting x squared again, and then, of course, minus 3. Notice that this is the exact same rule as the original. So f of negative x equals f of x. In other words, it doesn't matter if you plug in a positive or negative number into this function, you're going to get the same output. Right? If you plug in 5, you're going to get 22. If you plug in negative 5, you're also going to get 22. If you plug in opposite x coordinates, you're always going to get the same y coordinate. That's what this is saying in general. If you plug in negative x into the function, you'll get the same thing as if you just plug in regular x. This means that the graph is symmetric. It's an even function, first of all, but it's symmetric about the y-axis. Now we're going to use technology to see this symmetry. I've taken the liberty of typing in most of these functions already. I just now need to reveal them. So the first one is f of x. And notice the symmetry. This is symmetrical across the y-axis. This is called an even function. Okay, let's go to the next one. G of x equals x cubed minus 3x. Plug in negative x and see what happens. Each of these x's needs to be replaced with a negative x, and use parentheses, and then determine which negatives are going to remain, which ones are going to cancel. Well, when you cube the negative will stay, because negative 1 times negative 1 times negative 1, still negative. And then, of course, the x gets cubed as well. And here we do negative 3 times negative x. Those do cancel, giving us plus 3x. Is this the same thing as the original? And the answer is no. If they're not identical, try factoring out a minus sign and see what's left. There'd be an x cubed minus 3x. After you factor out a minus sign, is what's left in the parentheses the same thing as what we started with? And the answer is yes. So this is the same thing as negative of g of x. It's just the opposite of what I started with. This means that we have an odd function. Odd functions are symmetric about the origin. Here's our image. If you were to take this graph and rotate it 180 degrees around the origin, it would wind up producing the same image. Or if you were to reflect this graph around the y-axis and then reflect that reflection around the x-axis, you'll get back to this blue graph that we're seeing here. Symmetry around the origin is what we say, but this is an odd function. Sometimes we call this an odd symmetry. Now you'll notice why we say the words even and odd. It just so happens to be that if all of the powers on the x's that you see are even, this has no x, but sometimes people will force an x raised to the 0 to be attached to that, because x to the 0 is 1. Notice the powers on the x's. They're all even. An even power on a negative is the same thing as an even power on a positive. So when you plug in negative x, the even powers will negate that negative effect. So you get the same result as if you just do f of x. And so this is why we call this an even function. Look at this one here. There's an implied 1 on that one, and the obvious 3 on the other one, but all the powers are odd. A negative raised to an odd will remain negative. So all the terms will change sign when you plug in a negative. That's the same thing as if a negative was distributed through in the first place. And so we get the opposite y-coordinate when you plug in the opposite x-coordinate. And we get the symmetry about the origin, and this is why we call this an odd function. First, let's look at h of x. Right away, notice that we have a square, which is an even, and then a 1, which is odd. So we have a mixture. Let's see what happens when I plug in h of negative x. H of negative x is equal to negative x in parentheses squared minus 3 times parentheses negative x. Now, the first negative will be canceled by the square, leaving just x squared. But the next negative will remain, making this a plus 3x. So I'm going to stop right here. Is this the same as what I started with? The answer is no. Well, then factor out a minus sign. And that's just going to change the signs of both of these terms. And is what's inside the parentheses the same as what I started with? And the answer is still no. Neither this that's in the parentheses nor this is the same as the original. It's not equal to the original, and it's not equal to the opposite of the original. This function is neither even nor odd. And again, the fact that it had a mixture of parities of powers, one power was even, the other one was odd, because it had a mixture, then this is a neither situation. Here's the graph of h. The green one is not symmetric across the y-axis. It is symmetric around a different line, but it's not symmetric about the y-axis. Nor is it symmetric about the origin. If you rotate this 180 degrees around the origin, it will not be the same graph. So this has neither symmetry. Okay, now we're going to explore some functions that are a little bit more complicated and see what we can determine. Let's do m of negative x. Let me rewrite this as negative 2x over just negative x minus 1. Okay, so our first assessment, is this the same thing as that? Well, currently they don't look the same at all. Now, it is very tempting to cancel these two negatives, and when I cancel those two negatives, then they do look alike. So maybe this is the same as the original. But you have to be careful when you're working with these fractions. This negative here cannot be canceled with that one until the denominator negative is factored out. Let me show you an example of numbers just to make sure that's clear. -4 divided by -3 plus 1. Well, -3 plus 1 is actually going to be -2, so really this is -4 over -2, which is just 2 in the end. Can I just cancel those negatives and recalculate? That would give me 4 over 4, which is 1. Notice it's not the same thing, because you cannot cancel those negatives unless you factor out a negative. So you could pull the negative off the 4 and then factor a negative out of the bottom. That leaves 3 minus 1. Then these negatives can cancel. But notice we're left now with 4 over 2. That gives me the 2 again. Some students will fall into the trap of canceling those and saying, oh, I got the same thing I started with, and that's not true. Let's go ahead and factor out a negative from top and bottom, and then cancel them. Pull the negative off the top, pull a negative off the bottom, that will switch that to x plus 1, and then cancel these. So this is what this particular function simplifies to. And now we're in a position to say, okay, is this the original? No, this isn't the original. They're not the same. Is this the opposite of the original? And the answer to that is also not true. This is not equal to the original, nor is it equal to the opposite of the original. If you do the opposite of the original, if you put a negative in front of a fraction, remember this about fractions. If you say -2/3, you can choose to commit that negative to the top or to the bottom, but not both. Don't do the mistake of putting the negative in both places, because then -2/3 would become +2/3, and that's not the same thing as -2/3. So if you're considering, hey, what does the negative of m of x look like? Well, we'll put a negative in front of this fraction and commit it to 1 or the bottom. Negative m of x will look like the following. A negative in front of a fraction, and it's 2x over x minus 1. And then from there, you can choose to commit the negative to the top. So you could say -2x over x minus 1. Or you can choose to commit it to the denominator. So if you commit the negative here to the denominator and distribute it, it'll look like -x plus 1. So these are the three ways that negative m of x might look like. And notice our result here is none of these three. That's why I'm able to say it's not the opposite of the original either. So this is a neither situation again. Here's the m function. If you reflect this graph around the y-axis, it will not match itself. If you revolve this graph 180 degrees around the origin, it will not match itself. So it doesn't have an even symmetry or an odd symmetry. Okay, now let's do n of x. Plug in negative x's for both x's. So we have 6 times -x squared plus 1 over negative x down there. The negative x in the numerator, right here, that negative will be canceled by that square, by that even power. So we just get 6x squared up top plus 1 all over -x. So right now I can say, hey, is this the same thing as the original? Are these the same? And the answer is no, they are not the same. So we know it's not the original. So this is not an even function. But the negative that's down there at that bottom could be pulled to the very front of the fraction while leaving the numerator the same. And this one is the negative of the original. So we have an odd function here. Okay, here's our image. I'm going to change the y-axis scale. If you revolve this graph around the origin 180 degrees, it will match itself. So this is the odd symmetry. And finally, p of x, p of negative x. Plug in negative x to the top, x, and then also all the other x's down here, use parentheses. Okay, we get -4x up top. In the bottom, we get the cube. On the negative, we'll keep the negative, so it's -x cubed. And then minus -x is plus x. If you pause, you'll be like, okay, this does not look like the original. So it's very tempting to say that we don't get the original. There's a lot of negatives here. I'm going to do some factoring of the negatives out and see what happens. I'm going to factor a negative out of the top and bottom. So factor that negative off the 4x. Factor a negative out of the both terms of the bottom. That leaves x cubed minus x. And then cancel those, both negatives that I factored out. All right, so when you do that, simplifying, it really just boils down to this. Okay, but this is the original, right? So it turns out that right here was the original in disguise, was after you simplify it by factoring negatives out and canceling them, we do get the original p of x. So this is an even function. Here's the graph of p of x, and it is a mirror image across the y-axis. So we have the even symmetry. The slope of the line connecting 2 points of a function, a comma f of a and b comma f of b, is called the average rate of change of that function over the interval from a to b. So here's an image, here's a function of x, passes the vertical line test. Take any 2 points on the function and draw a line that connects them and calculate its slope. If you recall the slope, you do the change in y divided by the change in x, delta y over delta x, or f of b minus f of a all over b minus a in this case. Right, this is my y2 minus my y1, x2 minus x1. And that gives you what's called the average rate of change. So the population in millions of a country is given in the table below. Find and interpret the average rate of change in the population from 1990 to 2000, and then from 1990 to 2020. All right, so this number here, this is millions. That's 120 million. All right, we could put year on the horizontal axis and put population on the vertical axis. So in 1990 versus 2000 versus 2020. In each year, we only have one specific population. So for the first one, from 1990 to 2000, I want to find the slope of this line. And then for the second time I find an average rate of change, 1990 to 2020, I want to find the slope of the line connecting those points. All right, so these are the two slopes I'm after. All right, for the red slope, we do the second y-coordinate, so I'm doing the 145, minus the first y-coordinate, the 120, all over the change in x-coordinates, which is 2000 minus 1990. So we get a change in population of 25 million people. We did that in 10 years. That comes out to 2.5 million people per year. It's saying that on average, between those 2 years, this country gained 2.5 million people per year on average. Now for the green slope, we do this y-coordinate minus that y-coordinate, so 153 minus 120, and then over the difference in years, that year minus that year. It's 2020 minus 1990. So we get a gain of 33 million people, and it happened over 30 years. It's 1.1 million people per year. So it was a lower rate of change. That's because the population gained a lot more in the first 10 years than it gained in the next 20 years. And this ends this unit.